Thanks for the introduction. So I'm very glad to be here to talk about the two techniques that I developed in my PhD at Stanford. So one is the deep compression to compress the neural networks to fit in mobile. And the second is EIE, the efficient inference engine that works on the compressed model to make it even faster. So a brief introduction of our group. So I'm currently a fourth-year PhD at Stanford, and Bill Daly is my advisor. He's also the chief scientist at NVIDIA. So in this talk, there's going to be two parts. The first part, so it's software and hardware co-design work. On the software part, I'm going to introduce deep compression to compress the deep neural network model to fit it fully on SRAM. So you don't have to go to DRAM. And the second part will be the EIE accelerator. Since the compression brings some irregularity for the computation pattern, I'm going to introduce this accelerator that works fully on the compressed model instead of on the original model. So yeah, so this is the background. As we all know, the deep learning is the next wave of AI, spawning a lot of applications ranging from image recognition, speech recognition, and natural language processing. So these are a lot of high-level applications that I spawned. But there is one problem currently. So the deep learning models are pretty accurate. So it performs pretty well, but the model is too large. So what is the problem of a large deep learning model? If a deep learning model is hundreds of megabytes, then App Store does not allow you to download an app without Wi-Fi if your app is more than 100 megabytes. So a lot of companies like Google, Baidu, Facebook are paying a large attention on the model size, the binary size of their model. For example, Andrew Ng told us that they are very sensitive to the size of their binary files if their apps contain deep learning models. And the second thing is for our hardware designers. So we are concerned about the energy consumption of running such deep learning models. So if a deep learning model is really large, it takes a lot of memory reference, and most of the energy is consumed by the memory reference instead of the ALUs, multiplication, and add, etc. As shown on this bar, memory reference can be 2 or 3 more orders of magnitude than ALU operations. So making the model small to reduce the memory reference is really the key to reduce the power consumption. Yeah. So on the other side, if we run it on the cloud, that will suffer from, say, network delay and power budget on data center TCO or user privacy to upload their images to the cloud. And also, if you tell ask the robot something, the robot has to ask the cloud and then return. That's like a children ask a question to his mom and then return to you. That's not the real intelligence. So you really want to run deep learning models locally on your phone or on your mobile gadgets. So these two solvers, the first one is deep compression that compress the model size by 35x to 50x with the same accuracy and also with the speed up. And also the EIE accelerator makes you able to run the algorithm offline with the real time and with low power. So I'm going to start with deep compression. So my advisor Bill already hinted that last time when he made the presentation, our flag was 6.9 megabyte for AlexNet accuracy. And he hinted that we are going to make a less than 1 megabyte deep learning model sometime. That was 1 month ago, and now we made that. It's only 0.52 megabytes, only 520 kilobytes. A model that can achieve the same accuracy on ImageNet as the AlexNet. So only half a megabyte model. And similarly for VGGNet, we have made it 11 megabyte, and then both with no loss of accuracy. So this makes all the weights fit fully on SRAM cache. So taking 2 orders of magnitude less energy consumption. Oh, thank you.
You have a fan.
Hello. So yeah, so let's delve down to see what exactly happening to make the model get so small. So the first thing is pruning. We are getting rid of those unnecessary connections in the deep learning models. This is a fully connected network, but it also applies to convolution neural network, recurrent neural network, RSTM, which I'm going to show the results later. So this is actually, the idea comes from the human brain. So when we were born, we have 50 trillion connections in our brain. And according to this research published in Nature, by 1 year old, we have 1,000 trillion connections in the brain. But as we grow to adult, we have only 500 trillion connections. So it means half of the connections are pruned away during our learning process as we grow up. We only keep those useful connections. So does the same methodology and procedure apply to artificial neural network? So I did the experiment, and it exactly worked. This is the number of parameters that I prune away on a AlexNet. So pruning away 50% of the parameters, we got no accuracy loss. And then as we prune more, without proper fine-tuning and retraining, the accuracy begins to drop with the L1 regularization or L2 regularization with a single pass. But with multiple passes and proper retraining, we are able to fully recover the accuracy. You see, there's no accuracy drop here when we are pruning away 90% of the connections in AlexNet. But if we prune more, the accuracy is going to drop. So this is exactly the point we want to operate at. So across these 4 benchmarks on the MNIST dataset and an ImageNet dataset, we can reduce ranging from 9 times to 13 times parameters without losing the accuracy. So this is a graph showing the redundancy and the actual needed, the truly useful connections in AlexNet and VGGNet.
How do you know that it's useful?
So that is done by.
No, it's okay. You obviously using AlexNet. If it's not AlexNet.
Yeah, I'm going to show the big gun later that more efficient than AlexNet that has no fully connected layers or convoluted layers.
You couldn't prove me, obviously, because you never could count all of them. It's entire universe of them.
Yeah, but I'm going to show as much as possible networks ranging from image recognition, machine translation, and image caption. Yeah, so this result first. So what does the unnecessary connections mean? For example, for the MNIST dataset, all the digits are written roughly in the center of the image. There's no pixels, useful pixels in the boundary. So this shows the sparsity pattern of the first fully connected layer in LANET 300 and 100. So the image has 28 by 28. So there are 784 in this direction in the matrix, and the first hidden layer has 300 hidden units. So this matrix is 784 by 300. And we can see clearly that there are 28 bands, and the distance between each band is 28. That corresponds to, from here to here, every 28 pixels, we are going to have some empty places here that doesn't affect whether this is 1 or 4. Here are all empty. That's to say that during pruning, the network has found that those neurons are not useful, so it got disappeared. So that result showed on images it worked pretty well. Then how about on RSTMs and RNNs and other language-related neural networks? So with proper retraining, we can see that the accuracy doesn't drop when we prune away 90% of the parameters. As of some examples here for NeuroTalk, which is an image caption neural network. For example, for the first picture, a man playing basketball, the original network says a basketball player in a white uniform is playing with the ball. And if we prune away the 90% of the redundant things, it says a basketball player in a white uniform is playing with the basketball. And for the second thing, it's pretty similar as well. A brown dog is running through a grassy field versus running through a grassy area. And a man riding a surfboard on a wave versus a man riding a wetsuit is riding a wave on a beach. So the baseline is from the neural talk model done by Audrey Karpathy in Feifei's group. And the prune model is applying my methodology on that network. But if we are too aggressive and prune too much of the original network, it's going to be fail. For example, a soccer player in the red is running the field. But when we prune 95%, it says a man in the red shirt and black and white black shirt is running through the field. It's kind of drunk, so. So we have seen image caption. How about machine translation and RSTM, RNN and RSTM? So this shows the accuracy with different number of neurons that we prune away. And this shows that after retraining, pruning and retraining, this is without retraining, this is with retraining, the accuracy can sometimes get higher. So this is really interesting thing we found during the experiment. So why does the accuracy can not only doesn't drop, but also increase? So that is because this reduced overfitting. Overfitting says we have too large model size capacity, so we have high accuracy on the training set, but we cannot generalize it on the test set. But pruning finds you the right model capacity, and sometimes can lead to better accuracy. So I know some researchers from Hong Kong are deliberately using this technique to enhance their performance on face recognition. So these are the redundant things that we found in the word embedding and the IFOG, the different gates in the RSTM. Those dark places means they are not useful, and those white places means that they are useful. So yeah, this is Google Translate. Yeah, so the next topic I'll talk about weight sharing. So as the second stage of the pipeline. So we already talked about pruning, and then the result of pruning is feed to the quantization and weight sharing pipeline. So the basic idea is this. So if we take a weight matrix, so if you are 2.09 and I am 2.12, then we are both 2. So everything with the same color share the same value. So we need only to store those indexes to the lookup table instead of store the 32-bit floating point numbers. And when we do the update, we first do a group by the same color goes to the same place and do a reduce function, and then times the learning rate and do the SGD update. That's a one iteration of the stochastic gradient descent cycle. As we can see, this is the distribution of the weights of the weights after pruning. So everything close to 0 are pruned away. So, and the red dots, the green dots are the linear quantization result, and the red dots are the linear quantization result. Exactly the name, the weights after weight sharing, they only pick from these values. For example, you have more values here, then you are denser here. You will have less values here, then you are sparser here. So this is a figure that describes the 8 different layers in AlexNet, and with the less number of bits, 8 bits, all the way to 2 bits, how does the accuracy change? So we can see the 3 FC layers are really insensitive to the number of bits. For example, at 8 bits versus at 2 bits, they have almost exactly the same accuracy, even if we are going to all the way down to 2 bits. But at 4 bits, looks like there is no accuracy loss at all. But the column layers are a little bit more sensitive with the less number of bits. So we are going down to 4 bits, the accuracy doesn't change. But if we are going down to only 2 bits, the accuracy drops significantly. So 4 bits seems enough for the column layers, and 2 bits seems enough for the FC layers. So that's to say, many parameters can be quantized to just 16 values if you have 4 bits. 2 to the 4 is 16. So 8 bits for conv and 5 bits for FC layer lead to no accuracy loss. And 8-4 quantization lead to only 0.1 top 1 accuracy loss. And if you're going really aggressive and you really want to save power for your embedded device, if you want to use 2-bit quantization, it's going to lose about 2% accuracy. It depends on your design space exploration and your need. So this exactly shows the number of the energy taken by a multiply operation with the different resolutions in the ARU versus the accuracy drop. So after the weight sharing. And this slide shows, so we have 2 techniques now. One is pruning, the other is weight sharing. Are they able to combine together and work well together? And the answer is yes. So showing on all the layers, there are 4 curves here describing the top 5, top 1 accuracy with a different number of bits, ranging from 8 bits all the way to 2 bits. So we can see that combining pruning and quantization works better than just using pruning with the higher accuracy. That is because pruning already removes those unnecessary weights and makes quantization actually easier. For example, in this figure, it roughly does a coarse grain quantization with the 2 bins. So first one, the first bin, the second bin. So actually pruning helped the quantization to work. And the last thing in the pipeline is the Kaufman coding, which is a very standard technique with lossless compression. That is because the idea is that the more, if a weight appears more in that bucket, we want to have less number of bits to encode that weight. But if that weight appears less frequently, we can afford to use more number of bits to encode that weight. This method gives very marginal gain to the compression, but it takes some resource. So we didn't apply this to the hardware design, but used the previous 2 methods into our hardware design. So combining all the compression pipeline, we are able to compress different networks ranging from 35 times to 49 times without loss of accuracy. So this one shows the comparison with how many parameters, the storage we need, compressed it down to say 5% with the pruning plus quantization, quantization only versus the cheaper SVD method. So pruning plus quantization can push the limit to really like 3% without accuracy loss. This is the detailed breakdown of different layers. What is the compression rate? So the next big thing I want to talk about is if you really want to go really efficient, the big gun is going to be applying deep compression on new network topology. So to make your network topology efficient first, and then apply deep compression on top of that. So collaborating with Berkeley, we developed this new network architecture called SqueezeNet. This is the basic building block of FIRE module, and this is how we combine different FIRE modules and making it a super deep neural network. This network is fully convolutional, doesn't have any FC layers, and it has the same accuracy as AlexNet, but we are able to make it only 4.8 megabytes before compression. And after compression, it's only 520 kilobytes, 0.52 megabytes. So that is 431 times smaller than the original AlexNet, but can achieve the same accuracy. So after applying the compression on the networks, we tested the speed up over on top of the CPU, GPU, and mobile GPU. Across these benchmarks of FC layers, we observed 3x to 5x speed up, and also 3x to 6x energy efficiency on these hardware platforms. So as a small conclusion, so smaller deep neural network means we need less communication when we are doing distributed training. And we can download easier for deep learning apps to download from App Store. And we require less bandwidth to update the model, say, to a Tesla self-driving car. And it's easier to deploy on embedded hardware with limited memory. So I also made a deepcompression.net, a web service that help app developers to do the compression on their deep learning model. So currently, I have an easy version which doesn't support retraining. So it is fast with a moderate compression rate, but with some loss of accuracy. In later, if we can afford to have model uploaded and have the data set, we can support the advanced version which supports retraining, which will have higher compression rate with no or very little loss of accuracy. But that one will take some time. So this is the current web service we have. So deep compression, we have presented the method to the whole pipeline to compress deep neural networks without lose the accuracy by getting rid of the unnecessary connections and quantizing the network and enforce weight sharing and finally apply Huffman coding. So we highlight the ImageNet. We can compress it by 30 times x to 49 times without loss of accuracy. So now everything can fit in SRAM cache and opens a new story for hardware design. So the second part of my speech will be talk about how do we utilize the cool feature that everything fits in SRAM and design a hardware accelerator to accelerate the deep neural networks. So this is the layout of our chip. It can support, this is the motivation why we are building this thing. So this is a sparse, indirectly indexed, and weight shared matrix vector multiplication accelerator. So the first feature is that everything fits in SRAM. It's 120x saving compared with if you have to go off chip to talk to the DRAM. And it also exploits the sparsity of the activation. Since after the ReLU function, about 30%, only 30% of the activation are non-zero after pruning and applying the ReLU function. So it doesn't make sense to waste your computation to work on those zero elements. So we have a smart technique to avoid computation on those zero activations. And last thing, it works on the compressed model. So we have 30 times less work to do. So we distribute both the storage and computation across different processing engines, which can support different problem size. Maybe you have a smaller network, I have a larger network. We can just use different number of PEs to cater for both scenarios. And finally, we evaluated the EIE engine on a wide range of models and compared them with the CPU, GPU, and other accelerators. So this is the high-level structure of EIE. It has different amount of PEs, and this is how we distributed the computation and the storage across different PEs. Each PE have the same color, and they are partitioned by the row. So when we have a new activation coming here, we are going to pick only those non-zero elements. So those elements are stored in the CCS format, which is everything is stored densely to make the memory reference more efficient. And this is the building block within the single PE. Within the single PE here, this is the data path. We convert virtual weight and decode it to real weight, and we accumulate the relative index to get the absolute index. So this here, we have only 4 bits storing the weight and 4 bits storing the index, which is super compact. And finally, we evaluated with the standard ASIC design flow. We first built a cycle-accurate C++ simulator, and then coded the RTL in Verilog, and compared the result with the simulator as a golden model. And then we synthesized with the design compiler under the TSMC 45 nanometer GP standard VT library with the worst corner case. Finally, we do the place and route with ICC and annotated the toggle rate and dumped the safe file to estimate the power using the prime time PX. And this is the benchmarks and hardware platforms that we use to compare the performance of EIE. And this is the layout and also the power consumption and area of a single PE. So across these benchmarks, we have seen this just now. Now we just added another bar, which is the red bar. So it is 189 times faster than the CPU baseline. And it's a 24,000x faster, more energy efficient than the CPU baseline. And compared with the GPU, it's roughly 3,000x more energy efficient than GPU, and roughly 10 times or 10 to 20 times faster than a GPU with running the uncompressed neural network. So we may wonder, where does the 3,000 times energy efficiency come from? So first, there are three factors contributing to the energy saving. The first one is the matrix, the weights are compressed by 35 times. That is like if you're carrying bricks, you have less work to do, you have less bricks to carry. The second thing is that we don't have to go off chip to the DRAM, but access everything locally in our SRAM. So we don't have to go off chip. That's 100 times energy saving. That is like, we no longer have to carry bricks from San Francisco to New York, but only have to carry them from San Francisco to San Jose that have shorter distance. And finally, we take advantage of the sparse activation, which saves 3x the computation. That is like we have lighter weight bricks to carry. Previously, 100 kilograms, now only 30 kilograms. So this is the detailed benchmark wall clock cycle on different benchmarks and hardware platforms. And we have to mention that it is pretty scalable, all the way up to 256 processing engines. And we have a specialized buffer to deal with the load imbalance with and very good scalability. So the final utilization can be up to 90% to 95% utilization. And we have carefully chosen the SRAM width and also the arithmetic precision to achieve the optimal energy consumption of the whole system. So a little coverage from the next platform and already about compression and Hacker News. So yeah, as a conclusion, we present the EIE engine, which is an energy efficient engine that operates on the compressed deep neural network model, which reduced the energy by 3,000 times. So with the proper wrapper logic on top of EIE, this convolution is also achievable. So as a recap, so we have gone through the PC era to the mobile era, all the way we are now entering the intelligent mobile era. And we have plenty of room to explore the new hardware and new software in the intelligent mobile era to see a world that really powers the deep learning and all the applications with super efficient hardware. And thank you.